Hi everybody, Mr. Gerhard here, and this is a quick video on exponential and logarithmic models to solve word problems. Basically, a model is an equation that we can use to predict values in the future or based on information that we've already gained. Exponential models kind of appear like exponential equations. And this is a common one that we would use, an exponential growth model. There's four parts or four variables. N of t is the size of the population at time t. N sub 0 is our initial amount or initial size of the population. R is the rate at which they're growing, and t is the number of years usually, or it's the time that it's growing. If the rate is in something like 40% per hour, like it is in this example here, then our time would be in hours. But typically, if we're talking about human populations, we're talking about a growth rate per year, and that would be then in number of years. So there's four variables. We're going to be given three of them in the problem. We need to then solve for the fourth. So let's do an example. First example here says the initial bacterium count in the culture is 400. That right there means N sub 0 is 400. Biologist later makes a sample count of the bacteria in the culture and finds that the relative growth rate is 40% per hour. Growth rate, 0.4, is 40%. As a decimal, is 0.4. Using the exponential growth model, find a function that models the number of bacteria after t hours and use it to estimate the bacteria after 10 hours. So we know that we need to figure out N of t, and we know, that t is equal to 10. So using our model that we have over here, we can say N of t equals N sub 0 e to the RT. It's just kind of like PERT. A of t equals p e to the RT. It's just we're using different variables. And in our case, we want to find N of t with an initial value of 400 and a rate of 0.4 and varying amounts of time. So there's our model. That's the first part. Second part is what's the population after 10 hours? Well, that just means we're going to plug in 10 for t, and that gives us 400 e to the 0.4 times 10. If we plug that all into our calculator, we get 21,839. And so after 10 hours, there's about 21,800 bacteria because they wanted to know to the nearest 100 as to how many we were at. So 21,800 bacterium. Now that's one way that we can solve this problem. Another type of problem like here would say, well, how long until we reach 50,000 bacteria? That's essentially our question. Again, same idea. We're going to do N of t equals N sub 0 e to the RT, knowing that we started with 400 bacteria and that the growth rate was 40%. What's going to happen now? Well, we want to know what t value will give us a population of 50,000. So we're going to plug in what we know. 50,000 equals 400 e to the 0.4 t. Now we got to solve this exponential equation. We got a variable in the exponent, and so we're going to have to get this exponential term by itself and take the logs. So I'm going to do 50,000 divided by 400. And 400e to the 0.4 divided by 400, that will cancel out the 400s, and I believe it gives me 125 on the left. Now, if that wasn't a nice number, we would keep it as a fraction, and you'll see that a little bit later on as we go through. To get rid of the e, we're going to take the natural log, so I'm going to say the natural log of 125 equals the natural log of e to the 0.4 t. And then this natural log of e to the 0.4 t just becomes 0.4 t. The left side is still natural log of 125. I'm not going to put that as a decimal just yet because I want to get t by itself. I'm going to do that by dividing by 0.4 on both sides. And so really I'm going to get t equals the natural log of 125 divided by 0.4. And this is the exact value. But when I plug it into my calculator, I get 12.07. And so it's going to take us 12.07 days, or a little over 12 days, for this bacteria population to get to 50,000. Big thing, don't use decimals here so that we can get an exact answer. If we round a number here, when we plug it into our calculator, and then we do this and we plug it into our calculator and round again, this is going to be off by a little bit. Another type of exponential model is the radioactive decay model. Same idea. M of t is the amount or the mass of a radioactive substance after t days or t hours or t time. M sub 0 is the initial amount. R is the rate of decay, and T is the amount of time. Now this is kind of special because usually we calculate radioactivity in terms of half-life. Polonium-210 has a half-life of 140 days. And what that means is it takes 140 days for half of that to disappear. Well, when we do that, this R value, or rate of decay, is found by doing the natural log of 2 divided by h. And so when we have a half-life, like we do up here, h equals 140 days, we're going to use that in our R value. So polonium-210 has a half-life of 140 days. Suppose the sample substance has mass of 100 milligrams. Find the mass remaining after 1 year or 365 days. They give this because they know the half-life is in days. We want to keep the units the same. So writing down what we know M sub 0 is 100. We know H is 140 days. And because of that, we know that R is equal to the natural log of 2 divided by 140. So we'll keep it like that. And we know T is equal to 365. So plugging in what we know, M of T equals M sub 0 e to the negative RT. I'm going to say M of 365 equals 100 e to the negative natural log of 2 divided by 140 times 365. Looks kind of confusing to plug into your calculator, but you got to be a little careful as to how that works. Make sure that you put exponents or parentheses around the exponent here, and I would make sure that you put parentheses around that there. If you plug it into your calculator correctly, which I recommend that you do right now just to make sure that you get it right, is 16.4. We're talking about how much is left after 365 days, and so our answer is in milligrams. If you got something other than 16.4, you want to really check how you plug this into your calculator and see if you can adjust it so that it works out. This example is one about Newton's law of cooling, which we did the experiment about. So this should be pretty straightforward. The 210 degrees Fahrenheit is our initial temperature. So that's 210. We're placing it in a room that's 85 degrees. So the T sub S is 85. I need to know D sub 0, which in this case is T sub 0 minus T sub S. And so in this case, it's 210 minus 85, which is 15 to 125. We don't know K, but we do know that after 20 minutes, the temperature was 140 degrees Fahrenheit. And so really we know T of T right here, and we know 20 was T. What we can do then is use that information to find K. So plugging in what I know, let me just slide this over a little bit. I'm going to just use that as what we know. We know that T of 20 was 140 degrees. And we know T sub S was 85. We know D sub 0 is 125. We know E is E, the number E. We know K is what we're trying to find, and we know that it took us 20 minutes to get to this temperature. So I plugged in everything that I knew. I knew the temperature after T minutes, I knew T was 20, I knew D sub 0 and T sub S, and now I need to solve for K. To do that, I subtract 85 from both sides, giving me 55 over here on the left equals 125 e to the negative 20k. So divide both sides by 125, thus canceling that out there. I know this reduces 55 over 125, but I'm going to keep it as is just because if it doesn't reduce nicely, we're going to really want to make sure to keep it as is. So I'm just going to keep it like that. Now to get this variable out of the exponent, we're going to take the natural log of both sides, thus giving me natural log of 55 over 125 on the left and negative 20k on the right, because the natural log of e to the x is just x, and so there's my exponent. Then to get k by itself, we divide both sides by negative 20. That will leave me with k equals the natural log of 55 over 125 divided by negative 20. Now, hopefully you haven't plugged anything into your calculator until right now. Once you plug that into your calculator, you get 0.041049. And that's our constant. We're going to plug that back in and use that information. But this here, without doing any rounding beforehand, here or here or here, gives us the best answer. And so there's my k value, 0.041049. What I'm going to do now, I'm going to go on to the next page, and we need to know what the temperature is after 25 minutes. So again, I'm just going to plug in what I know. T of T equals T sub S plus D sub 0 e to the negative KT. That's our Newton's law of cooling formula. I'm looking for the temperature after 25 minutes. I know the temperature of the surroundings was 85 degrees. I know D sub 0 is 125 degrees. I know now that K is 0.041049 and T is 25 minutes. The nice part about this is I simply plug it all into my calculator, and when I do that all at once, I get 129.8 degrees Fahrenheit. And so that is the temperature after 25 minutes. Finally, there's 3 different logarithmic scales that they talk about in your book, and I would look at examples on page 376 to 379 on how to work with some of these. The simplest one is the pH, because you've been working with that in chemistry, I'm sure. The pH of a substance is equal to the negative log, common log, of the concentration of hydrogen ions. And so they're going to give you this most likely and ask you to find the pH, or they'll give you the pH and ask you to find the concentration of hydrogen ions. The Richter scale and decibel scale are a little bit trickier, and so I'm going to let you take a look at those examples, and we'll talk about those a little bit more tomorrow. But this right here is talking about the intensity of a earthquake, and because it's a logarithmic scale, for every one value it goes up on the Richter scale, it's increasing, or it's a 10 times more intense earthquake. And very similarly with the decibel scale, where I is the intensity and I sub 0 is the initial intensity. So take a look at those, and good luck.